today we're going to study reaction kinetics. When we talk about reaction kinetics, what we're doing here is we're studying the rates of chemical reactions. Okay, reaction kinetics refers to the study of rates. Okay, so specifically we're going to be studying the rates of different types of chemical reactions and chemical processes. Now, how do we define rate? Rate can be defined as the change in the concentration of a substance. Okay, the change in the concentration of a substance. You can say the change in concentration with respect to time. Okay. And the units for rate will be moles per dm cube per second. Okay. Moles per dm cube per second. Those are the standard units we're going to use for rate, right? Change in concentration. Concentration as units of moles per dm cube, and then time in seconds, right? Sometimes time will be given in minutes. So then sometimes the rate may be reported as moles per dm cube per minute as well. So now let's say I have an example of a reaction where A and B react to form C and D. Okay, A and B react to form C and D, right? Now, let's say that every second the concentration of A is decreasing by 2 moles per dm cube. Okay? Every second the concentration of A is decreasing by 2 moles per dm cube. Okay, so this is the rate at which A is decreasing. Okay, the rate of decrease is 2 moles per dm cube per second. So every second the concentration decreases by 2 moles per dm cube, for example, right? Similarly, for C, you can say that the rate of production will be 2 moles per dm cube per second, right? At some given point in time. In this reaction, I notice that A is decreasing at 2 moles per dm cube per second and C is increasing at 2 moles per dm cube per second, the concentration, right? Now, as far as the rate of the reaction is concerned, I can use any one of these measurements to report the rate of a reaction. So for example, over here, right, let's say that this was experiment 1, right? In experiment 1 mein, at t equals 0, right, I had this rate of decrease of A and this was the rate of production of C, right? This was the rate of production of C. Now what I can say is that, let's say experiment 2 mein, right, what I did was I said, okay, yaar, I want to know the effect of the concentration of A. I want to know the effect of the concentration of A on the rate of the reaction. So for example, let's say I double the starting concentration of A. I keep the same concentration of B. That will tell me the effect of the concentration of the reactant, right? So let's say in t equals 0, in the second case, I say that the rate of decrease of A was 4 moles per dm cube per second. So what I did was I simply doubled the concentration of A and I had twice the rate of decrease, right? Similarly, the rate of production will now be 4 moles per dm cube per second, right? Now, in a table, for example, I might say experiment 1 and experiment 2, right? And I'm going to report the rate for these different experiments. I could for all the experiments, since I'm comparing different experiments for the same reaction, I can report the rate using the rate of production. So I can say the rate is 2, 4, 6, so on, or I can report the rate using the rate of consumption. It doesn't matter which of these two I report, because if this will be consumed twice as fast, then this will be produced twice as fast, right? If I double the rate, then all the reactants will be consumed twice as fast and all the products will be produced twice as fast. So it doesn't matter, अगर मैं आपको rate का data दूं, I can give you rate of production or rate of consumption. You're only concerned with the relative effects. You're only concerned with how does experiment 2 compare to experiment 1, and you can look at that using either of these two data. You can easily see that experiment 2 is happening twice as fast at the beginning as experiment 1 by looking at these 2 points, or you can see that by looking at these 2 points. As long as मैं throughout सारे experiment में same चीज़ का report कर रहा हूँ, तो मैं अगर मैं मुसलसल सिर्फ C का report करूँगा, तो मैं या फिर मैं सारे एक्सपेरिमेंट्स में A का रिपोर्ट कर सकता हूँ या सारे एक्सपेरिमेंट्स में B का रिपोर्ट कर सकता हूँ and so on. Okay, so when you see a table like this with the rate, this could have been any of the things. It could have been any of the products की rate की production की rate या any of the reactants की consumption की rate. Yeah, if they just give you rate, they won't. Sometimes they won't specify किसकी rate monitor कर रहे थे, but they will give you rates की values. It could have been any of these, but essentially your job will be to compare different experiments, and you can do that by looking at data for C, by looking at data for D, for A, or for B. Now, if you look at collision theory, what we say is that particles are constantly in motion and they collide into each other, right? And if they collide into each other with enough energy, right, energy that's greater than or equal to the activation energy, and they collide in the right orientation, a reaction will take place, right? So if they, for example, collide head on with enough energy, a reaction might take place. So it's collisions between particles that result in chemical reactions. And specifically when we talk about a collision that results in a reaction, we call that an effective or a successful collision. Call that an effective or a successful collision. An effective collision or successful collision is a collision where particles collide with energy greater than or equal to the activation energy. In other words, an effective or a successful collision results in a chemical reaction. And we can say that the higher the frequency of successful collisions, or the higher the frequency of effective collisions, the higher the rate, right? Again, the frequency of successful collision simply means, right? Frequency of successful collision means successful collisions per unit time. So for example, if I have 500 successful collisions per unit time, I'm having 500 reactions per unit time, right? If I have, let's say, 1,000 collisions per unit time, right? Successful collisions per unit time, that means I have 1,000 chemical reactions taking place per unit time. So jitne zyada, the greater the number of successful collisions or effective collisions taking place per unit time, the higher the rate. And if you guys remember, the activation energy is, you may have learned this as the minimum energy needed for a reaction to take place, but more precisely, when we look at collision theory, we can say that it is the minimum energy needed for a collision to be successful. Minimum energy needed for a collision to be successful or effective. So when asked to define the activation energy, this is how you would define it. Okay, it is the minimum energy needed for a collision to be successful or effective. Now, when we talk about the frequency of successful collisions or the frequency of effective collisions, again, we're saying that the greater the frequency of effective collisions, the higher the rate, right? So frequency of effective / successful collisions, right? When we talk about that, we're really talking about the rate, right? Now, when we talk about the frequency of successful collisions or effective collisions, there are two things that we're looking at. The first thing that we're looking at is the frequency of collisions. The frequency of collisions. This is the total number of collisions that are taking place per unit time. Okay, the total number of collisions per unit time. So, for example, let's say that I have a reaction where I have 100 collisions taking place per unit time. Okay, for example. And the second thing that we're going to look at is the success rate. What percent of collisions actually result in a chemical reaction? What percent of collisions actually result in a chemical reaction? So in this case, for example, let's say I have a certain reaction that we have 100 collisions taking place per unit time, but only 2% of those collisions are successful. So then how many successful collisions are taking place per unit time? 2, right? So let's call this case 1. We have two effective collisions. Okay, I'm just going to call that EC for now. Okay, two effective collisions, right, per unit time. So that's the initial rate of the reaction. Now I can increase the total frequency of the collision, Okay, instead of having 100 collisions take place per unit time, I can say let's have 200 per unit time. 200 collisions. Success rate वही है. Success rate वही है, right? I can do that by having more particles present or increasing the speed of the particles. Okay, more particles present per unit volume or increased speed of the particles. Okay, so now again I have a 2% success rate, but now I have 4 effective collisions taking place per unit time, right? So that will be your case 2. So I have 4 successful collisions taking place per unit time. Okay, or 4 effective collisions taking place per unit time. The third thing I can do is, instead of affecting the frequency, I can also increase the success rate. I can increase the success rate also, right? I can say instead of having 5 instead of 2% of all collisions being effective, what if I had a 5% success rate? Okay, I keep the same number of collisions. I still have 100 collisions taking place, but pehle only 2% of them resulted in a reaction, and now 5% are resulting in a reaction. Again, that will also increase the rate. Now, what factors affect the success rate? When we talk about the factors affecting the success rate, right? Essentially, to increase the success rate, what we want to do is we want to increase the average energy of the particles, right? We can do that by increasing the temperature. So now we'll have more particles with energy greater than or equal to the activation energy, and therefore we'll have a higher success rate. More of the collisions will result in a reaction taking place. Or what we can do is we can lower the activation energy. If we lower the activation energy, then particles with lower energy will have enough energy to react, and therefore again, even if you were having 100 collisions taking place, right, we will have more of those collisions resulting in a reaction, because the lower energy particles would also result in a reaction. So temperature is the only factor that affects both frequency of collisions and success rate. Okay, whereas pressure, volume, for gases, concentration and surface area affect frequency, and catalysts only affect the success rate. The first factor that we're going to look at is temperature. Okay, so we're looking at the factors affecting rate. And the first factor that we're going to look at is temperature. Okay. Now, before we look at the effect of temperature, before we talk about it, let's look at the Boltzmann distribution, right? This is from your AS theory. So if you guys remember, right, this is the Boltzmann distribution where we plot the number of molecules against the molecular energy, number of particles on the y-axis, and this is the energy on the x-axis, right? And let's say this is the curve, right? This is a curve at temperature T1. Okay, this is our curve at temperature T1. Okay, so this is, let's call this temperature T1. Okay, and now we have a curve like this at temperature T2. Okay, so let's call this temperature T2. And here, let's say this energy is the activation energy. So this is the minimum energy needed for the reaction or for the collision to be successful, or for a reaction to take place, right? So this is the activation energy. Now we can clearly see from the graph that T2 is greater than T1, right? We studied the Boltzmann distribution, and we know that if we increase the temperature, this curve sort of shifts to the right. In other words, on average, the energy of the particles increases. And what we can see in terms of rates of reaction, if you guys remember, the area under the curve represents the total number of molecules, right? So if you look at the area, under the curve right here, right, above the activation energy, this area tells you the number of molecules that are reacting successfully per unit time. And if I increase the temperature, I simply have more molecules reacting per unit time, right? So initially I only had this number of molecules reacting per unit time successfully. Now I have this number of molecules reacting per unit time successfully. And when we talk about temperature, what we've done is, right, when we increase the temperature, if I increase the temperature, what do? I first of all increase the speed of the particles, right? So if I increase the speed of the particles, it means that therefore the frequency of collisions increases. frequency also increases. I have more collisions taking place per unit time, right? And what I've done is if I increase the temperature, I also increase the kinetic energy, right? Temperature is just a measure of the average kinetic energy. So if I increase the kinetic energy, I can also say that more particles have energy greater than or equal to the activation energy. So what I've done is I've also increased the success rate. Right? Because now I have more particles with enough energy to react. As a percentage, as a proportion, I have more particles with enough energy to react. So as an example, initially I might have had just 2% of particles reacting. After increasing the temperature, I have a greater number of particles reacting successfully. Because remember, Boltzmann distribution where the area under both curves is the same, right? So the area under both curves is the same, right? But now a greater proportion or a greater fraction of particles are reacting successfully. So because more particles have energy greater than or equal to the activation energy, we can say that the frequency of successful collisions increases. Frequency of successful collisions increases. And therefore the rate of the reaction increases. Now, because temperature has such a significant impact on the rate, what we can see here is that the rate tends to increase exponentially with temperature. Okay? So the graph would look something like this. All right. So if I increase the temperature, the rate increases exponentially because. So now we look at the next factors affecting rate. Okay? We're going to look at concentration. Okay? Pressure for gases. And surface area for solids. Okay. They all have a very similar effect. On the rate. Okay. So the first factor that we looked at was temperature. Okay, and temperature only affected the frequency of collisions as well as the success rate. When we talk about concentration, pressure for gases, and surface area, these are three different factors. Okay, so there's factor two. So now we're looking at a total of 4 factors. We looked at temperature, and now we're looking at these 3 factors. Okay, together. And these guys, what they do is they increase the frequency of collisions. Okay? They increase the frequency of collisions. Okay? And they increase the frequency of collisions because more particles are present. More particles present per unit volume. If there are more particles present per unit volume, it means that the frequency of successful collisions increases. Okay? Frequency of successful collisions increases. Now first let's look at concentration. So here, for example, let's say that I have a solution, right? I have a solution and there's a certain number of particles present in the solution, right? Let's say 4 particles here, the way I've drawn it. And what I've done is I've simply increased the concentration by increasing the number of moles of particles. Okay, so I have the same volume, but now I have more particles present. Right? Again, these particles are moving around at random, they're colliding with each other, and some of those collisions will result in a reaction if they collide with enough energy. Right? Now, because more particles are present, there's just a higher likelihood of them colliding. So the frequency of collisions increases, right? So even if you have the same success rate, because you haven't increased the energy of the particles, because there's more collisions happening per unit time, there's simply going to be more reactions happening per unit time. So there are more particles present per unit volume. So that's the effect of concentration on the rate of a reaction. Okay, it increases the frequency of collisions. So the frequency of successful collisions, therefore the rate increases. Okay. Now we're going to look at pressure for gases. Okay, so let's say I have two different systems. Okay. In the first case, let's say that I'm applying a certain pressure P. Okay, and in the second case, let's say that I've doubled the pressure. Okay, and in both cases, I have the same number of particles. Okay, I have the same number of particles, right? And what I can see is that if I double the pressure, right? If I double the pressure, what that means here is that I have the same number of particles occupying a smaller volume. Now, if you guys remember, concentration is simply the number of moles per unit volume, right? So if I increase the pressure, all I'm doing is I'm simply decreasing the volume, same number of moles or same number of particles, so I've increased the concentration. So pressure and concentration have, pressure for gases is basically the same as concentration. Higher pressure means higher concentration. Okay? So I can directly increase the concentration by increasing the number of moles. If I have more moles of gas present, I'll have a higher concentration, so more collisions will take place. Or I can just decrease the volume by increasing the pressure, and again, I've increased the concentration. So these two are very closely related to each other. Okay, and if there's a smaller space being occupied, even with the same number of particles, collisions are just more likely because they're moving around randomly. They have lesser space to move about. They're more likely to collide into each other. The last thing we're going to look at is surface area for solids. Okay, we're going to look at surface area for solids. And let's say that I have a solid, okay, that's reacting with particles in some solution. Let's say I have a solid that's reacting with some particles in a certain solution. And let's say that these are like the particles that are trying to react with the solid, right? Let's say that these are the particles that are trying to react with the solid. Now these particles are only exposed to the surface of the solid. They can only react with the surface of the solid. Now let's say that I slice the solid. I slice the solid in two different places, and I slice it into three bits, right? So I have the first bit, I have the second bit, and I have the third bit. It's the same solid, but I've broken it up into three parts. Now initially this was the surface of the solid that was exposed, right? I've highlighted that. If you look at the second case, I've highlighted that same surface here, right? The outer surface was exposed, but now we can see that these interfaces that were initially weren't available for reaction are now exposed, right? So this guy over here, right? This wasn't available, this wasn't available, this wasn't available, this wasn't available initially. So now what's happened is that I have simply increased, right, the particles of the solid present per unit volume of the solid, right? Now these faces of the solid, right, there are more places where the reactant, right, where this solution can react with the solid. Okay. So as a consequence, what happens is that when I increase the surface area, essentially the greater surface area to volume ratio, right? More surface area, more surface exposed per unit volume, and again, there will be more collisions taking place, and therefore the frequency of successful or effective collisions increase. The next factor that we're looking at are catalysts. And we know that catalysts are reagents that increase the speed of a reaction. They increase the rate of a reaction by providing an alternative pathway, an alternative mechanism with lower activation energy. So what a catalyst does is it increases the rate by lowering the activation energy. Okay. Now we can see that on the Boltzmann distribution here, why the rate increases when we lower the activation energy. Again, we have number of particles on the y-axis, or number of molecules, and we have energy on the x-axis, right? And here we have a Boltzmann distribution, of molecular energies. And this is the activation energy right here, right? Activation energy. And let's say that this is the activation energy without the catalyst. Right? Now we can say that if a catalyst is absent, over here, right, then this area over here represents the total number of molecules that will react in the absence of that catalyst, right? Remember, the area under the curve is the total number of molecules, and obviously these molecules need to have energy that is greater than or equal to the activation energy, right? They need to collide with enough energy to overcome the activation energy in order for them to react. So this area represents the total number of molecules that will react, or total number of particles that will react, right? If we add a catalyst, what we do is we lower the activation energy. So this is the activation energy with a catalyst. So now what we've done is, if we've lowered the activation energy, now we have more molecules present that have energy greater than or equal to the activation energy, right? So now this total area, this area plus this area, represents the total number of molecules that will react. Okay, so because we've lowered the activation energy, what that means is that now more molecules have or collide with energy greater than or equal to the activation energy, and therefore we can say the frequency of successful collisions increases, right? Frequency of successful collisions increases. So catalyst doesn't really affect the frequency of collisions, right? It affects the success rate, right? We have the same number of particles, we have the same frequency of collisions, but now lower energy collisions will also result in a reaction. Before you needed much higher energy, for a reaction to take place. Now, even collisions with lower energy will result in a reaction taking place, or will result in an effective, or will be an effective or successful collision, right? So therefore, we can say frequency of successful collisions